All right, so my name is Niall Douglas. I have been involved with Boost for probably actively since about 2012. I Boost Google Summer of Code admin for the last few years. It's my last year, actually. I'm going to resign at the end of this summer, and it's been an interesting program. I have been busy trying to get various libraries into Boost, and I've successfully failed, and that's better than unsuccessfully failed. So in that sense, I've successfully failed and got lots of very valuable feedback. And this is my next library, is coming up at the end of May for peer review. Now, it's a bit of an interesting one because it actually implements the forthcoming standard proposal for the standardization of stood expected. So this talk is exclusively about the standards proposal, and it's only right at the end that my library comes in at all. So I went off and I implemented what's planned to be standardized at some point soon for C++ 20 or so. So you might get a view onto what's happening. So we'll see what happens. Okay, so content. I'm going to firstly start off with an overview of error handling in C++, because we've got 30 years worth of error handling and how to do error handling, and fashions have come and fashions have gone, and different niches like games industry have a very different approach to error handling than, say, Boost does, which then has a very different approach to error handling than, say, high frequency trading does, you know. So I'm going to run through integer return codes. So that's good old-fashioned C return codes or from the assembler days. Exception throws, because, you know, we have to cover them. We move on to error codes, which came in C++ 11, which a few people are still surprised are actually in there. They actually came from Boost System originally back in the day, and they're great. And lastly, we got these lovely Mongrel Monads. I only use them because it's a catchy title, but it's not incorrect. They're not really proper monads. They're what C++ calls monads, which gets people who are keen on function programming really angry because they're very impure, and that's okay. I have even more mongrelized monads in the outcome library as an extension for games and SG14 low latency trading type stuff. In fact, Vicente just asked me this morning what makes my low latency stuff low latency as against his stuff, which is by implication is not. And we'll see what happens. So the next thing I'm going to do is I'm going to benchmark, because a lot of time we talk about error handling in the abstract. So I came up with a terrible but still illustrative benchmark of performance. I used GCC 6.2, Clang 4, and Visual Studio 2017. So I have some graphs. I quickly will talk about the convenience extensions to the WG21 proposal. I called them option, result, and outcome simply because that's what Rust and Swift call them. And then finally, rather than go into the monadic programming API, which would take an entire hour on its own, hour and a half, I'm just going to show some code examples if there's time. If there's not time, we're just going to skip them because they're just little puzzles to keep you all on your toes. All right, so C error handling. I hope everybody will understand this straight off without me having to explain it, but we'll see what happens. So the idea behind it, it stems from back in the days of good old assembler. I'm sure, like all of you, you all started off in 6502 assembler like I did. Believe it or not. And 6502 is great. You had a general accumulator register, and you used it to return error codes. And it's simply an integer between 0 and 255. On modern processors, it's up to 32-bit. But usually what you need to do is you need to indicate when you're passing between multiple libraries that code number 1 in this library A might mean something completely different from code number 1 in library B. So you need to usually supply a second integer or a pointer or some other way of describing them to indicate that they come from two separate libraries. And we're just going to call this a domain. So here's my red dot. Let's call it a domain. And that's what it is. It's simply what does the number mean. So there's lots of variance in the C integer pattern. Ideally, in modern C, you should be using an enum. You really should, rather than macros, and yet you'll still see lots of new C written that is using macros. On the other hand, enum has slightly more type safety, so that's good. You can do things like you can return the integer directly, so you'll see that in sockets APIs on Windows and stuff. Another way to do it is errno, which Marshall Clow was telling me yesterday. Apparently errno isn't actually guaranteed to be thread local, and yet I can't think of any useful errno that wouldn't be, but apparently it's not actually guaranteed. And then, of course, the Windows equivalent is get last error. And then lastly, there are quite a few APIs that return error codes via an int pointer, just because I guess they're using the return code for, or the return from the function for something else, which is So I should tell you that these slides are not great because yesterday I came to do a audiovisual test and I stood about 3 rows in and I realized that nobody would be able to read the code. So as a result, I have split the code out and doubled the font size, but it makes it really much less easy to understand. It's over multiple slides to have some idea of for people to be able to read it at all. So I don't know, can anyone at the back actually make that out? You can. Wow. Oh, yes, everyone's happy with it? Nobody? If you can't, you're going to have to move forwards because, I mean, 18-point text is the best I could do. Oh, sorry. So yeah, this should be really, really straightforward to anybody. In C, you're going to have a handle. You are going to have some sort of file descriptor, say. I'm going to do an open file example throughout. You have your enums, so here's your domain, so success often is set to 0 just because of convention. Let's say nomem is 1, not found is 2, and it runs on. So this is pretty straightforward. There's no complication there. Here's a little open file function I wrote in C, just to kind of illustrate kind of what's going on. You'll see one of these for every single type of error handling as we go along. So firstly, this will be an extern function. It's going to return an int. That will be your error code domain, I would assume, from the look of it. Yes. It should have actually been the enum, so there's a bug. That's okay. You write out to a struct handle pointer to outh, because handle pointer is the thing that's being generated by open file. So you're writing it out to outh as supplied by the caller. You take a const char path for which file to open. Over here, we write into outh a malloc of the size of the struct handle. If we fail to allocate the memory, we return nomem as the error code. Over here, we dereference the outh that we just wrote, and we write into the fd integer, open for the path, read only, just for a case of exposition. If that failed, so if outh fd is -1, then we free the memory we just allocated. We write into the thing that we just wrote, put that back to being null again, lest the code calling it gets confused, and we return not found. If we manage to get all the way down to here, we now return success. So I assume, has anybody not seen this code pattern before? Hands up, anybody who hasn't seen that before in their career to date. Oh, I was hoping for at least one. No, okay. So that's fine. So here's C++ 98, error handling. Yeah, I remember the good old days where we used to throw an exception for anything. I don't know if, it depends on how old you are, but I remember when exceptions first came into Visual Studio, it was Visual C++ back in the day, and you were like, oh, let's just throw them for everything. Anything at all, just throw an exception. Anyway, so yes, it's very straightforward. You should all hopefully be very familiar with this. If you have any familiarity with C++, some of you may not, of course. It's not a C++ conference, this strictly. Very simply, if there's an error, you throw an exception. A lot of code misuses them to do a sort of contract-based programming, so you test if the range of values coming into a function are between such and such list, and if you don't, you throw an exception. You see that quite commonly in the wild. It's not ideal, but it's not terrible, assuming that the range of functions aren't coming in particularly frequently. There is, unfortunately, a pattern where you see control flow, so I'm thinking of MFC and a few other older C++ libraries in particular that will throw C++ exceptions mainly as a control flow. And the interesting thing is that back in the early days of C++ exceptions, they were actually quite fast to throw. But what happened was that compiler implementers realized we could do a zero-cost table-based exception handling implementation, whereby if you never throw an exception, your code runs really, really quickly. But if you do throw an exception, you pay a very heavy cost. And it's very funny because nobody was actually really sure how much they costed. Even I asked some of the compiler vendors privately by email, and I said, how expensive is throwing a C++ exception? And nobody could tell me, because nobody had actually benchmarked it recently. They said, the last benchmarks we did on that were 2002, 2003. Modern hardware probably doesn't do as well. So I put together some benchmarks and I sent them around, and people were like, whoa, that's way more expensive than we thought. So you'll see there's a log graph coming, and that will give you an idea already of just how expensive we're talking. So here's the same open file implementation spread out over many slides. So over here, you will see if my dot returns. There we go. We have our struct handle again. We have our int fd. We call some sort of abstract base class, so you can just assume it is. We have a virtual handle destructor where if the fd is not -1, then we try to close it, and we set it to -1. So that's a standard kind of destruct you might get. And down here, I kind of cheated, and I simply said this is some sort of smart pointer handling a handle pointer. You can just assume it's a unique pointer or a shared pointer or something completely different. Who knows? Here's our open file function using C++ exceptions. So once again, it's extern. We're no longer writing out the particular thing that the handle, because we're now returning it. We now only take a path in. We no longer need to return error codes explicitly because we have an extra control path. So firstly, we open the FD, again, once again, read-only. If we fail to open the FD, we now throw an exception, std runtime error, file not found. This is C++ 98. There wasn't much more you could do. We do an RIII. I assume everybody knows what RIII is. Resource acquisition is initialization. So if an exception throws, we want this to get closed. That's why we wrap it immediately into a handle. That could throw a std bad alloc. So for example, if handle ref were implemented as a make shared pointer, there would be a memory allocation just here, or maybe during this new derived handle implementation, something throws, in which case it will kick back up here to temp. That will then delete the closed file handle, and everything unwinds, so as the exception gets wound back out. So does everyone understand that? Any questions about that? That all makes sense? You've all seen this before, I take it? Okay, cool. Can anyone say, just out of interest, because I like to throw little questions in, this is C++ 98. Can anyone say what that should be in C++ 11? Sorry?
STD file not found?
No, there is no STD file not found in C++ 11. You're on the right track. It's system, indeed. And could you say, for extra bonus points, how should you construct it? Nobody? Ooh, it's okay. I'll get answered later on. Sorry? Brace initialization you could do, but there's a very undocumented, it's very poorly documented how this stuff is supposed to work. You have to go back to the original blog post by the people who invented it back in the early 2000s to actually realize. And moreover, committee members consistently get this wrong. So it's one of those things that there's some on the committee who know how it works, and then the rest actually have to be educated. So it's actually that obscure. Both myself and going at this conference, you'll find at C++ Now, Charlie Bay is coming in and doing exactly the same talk to the guys over in North America, and we'll hopefully get the message through that it's different from what you think it is. But that's okay. That's good. I was just testing to see where people are at. Okay, so C++ 11's error handling, major leap forwards. We have the wonderful system error header. So who here before has used the system error header in their code? 1, 2. Oh, I see a cluster around, the people with yes, standard library experience. How interesting. The other thing that's kind of funny is, what does NoExcept actually mean? And it might seem a bit of a weird thing, but there's actually a debate amongst committee members about what does NoExcept really actually mean. There's its technical meaning, but what's its philosophical meaning? What does it mean to programmers? What's its semantic meaning? And that's a really interesting debate. You can actually get into multiple week-long email conversations about what does NoExcept really actually mean. So I will just give you what I think it means, and I won't even enter into the debate. So system header, it actually comes straight out of Boost. My best guess, and I may be completely wrong, the committee members may be able to correct me, but I think it was Beeman who came up with it. Believe so. That's our best guess. People's memories is a bit fuzzy at this stage. But Boost system was basically a method of wrapping up C integer error codes in a type-safe fashion in C++. So it's exactly the same in terms of underneath the bonnet representation. There's an integer and there's a pointer. You couldn't say it was any different. It has the same lightweight cost. So it was simply brought in, pretty much as is. Very, very little was changed, apart from maybe to slightly improve the interaction with C++ exceptions, because now we had std current exception now worked. So what you have, basically, how it works, it's very straightforward. You have these singleton subclasses of some implementation of std error category. You can, by the way, add your own. You can completely extend this with any custom error category codes you want. The standard library comes with 4, I believe, off the top of my head, already built in. But it's entirely up to you. And of course, Boost could extend these, or anybody could extend these. In fact, if any of you have used networking TS, which is ACCU, it extends it with its own custom error codes. That's straightforward. As I mentioned, a std error code is an integer and a reference, so it's just a pointer to some error category singleton. So very, very straightforward. And what you'll find is they've nicely added std system error, which was mentioned by someone in the middle, that subclass is stood exception to transport an arbitrary error code as a payload. So the idea is that if you have a stood error code, you can now wrap it up into a C++ exception, throw it, it can get caught, they can extract back out the error code again and do stuff with it. So that's pretty straightforward. It's kind of funny because for something that had been around for so long, there's actually very little in the standard library that actually uses it in C++ 11 or C++ 14. It's almost entirely unused. It's just there. It's not even hugely widely used in Boost libraries, interestingly enough. File System, which is a Boost library originally, does use it, and it's coming in. ACCU, which is coming from Boost, it's also coming in standard, and it's also very heavily uses error codes. So I would imagine, I've had some conversations with some people off Stands Committee about getting things like stood vector to return error codes. So in other words, they would provide overloads. So for example, pushback at the minute might throw an exception. The idea is that you would have a pushback overload that took an error code that would say, well, I failed to allocate memory, so I'm not going to throw an exception, I'll set the error code instead. Now, whether that ever comes to pass, I don't know. It would be an interesting advantage. Once you see how expensive throwing exceptions is, you're kind of going to go, maybe there's a use case for this, you know. So one of the things that's really clever about the system error design, it's much more clever than it looks on the surface. It's only when you really get into it, you realize how clever it is. One of the great advantages, which, as I say, people consistently get wrong even on the Standards Committee, is that there's a semantic framework mapping. Same as C++ exception throw. So when you throw an exception, you don't have to catch the exact type that was thrown. You can catch a subclass of that type. Because you find the compiler will go off and do a match, and it will figure out, can I convert this down, and as a result, match a particular catch. And that lets you implement a form of semantic mapping, because you can group and categorize errors under particular categories. You can do exactly the same thing with error codes. So the idea is that there's a stood error code, and that is your raw error code with its category. And you also have a thing called stood error condition. It's really unfortunate that it had to be named stood error condition, because if it had been named something a bit more clear, it would be a bit more obvious. But stood error condition is called a portable error code in the standard, which it is not. And in fact, what it really is a semantic map. So it is a generic mapping which applies on all platforms. So for example, file not found. And what you'll find is on each different implementation system, so on Windows, that you'll take the error code that it is file not found on Windows, and it will happen to map to the file not found error condition. Similarly, if you're on POSIX, you'll find that the error code that's there for POSIX will happen to map onto the error condition for file not found. So this is a way of you writing completely generic code that works on all platforms equally. So it's very clever. If you're doing switch maps, which you'll find often in any larger program where you're dealing with error codes from, say, OpenSSL, and you're dealing with error codes from a different library, you'll find there's these switch maps where huge switch statement with each of the error codes coming in, and you'll map them to error codes going out. If you're doing that with C++ 11, you're doing something very, very wrong. So this is my best way, and this is unfortunately the smallest font in the entire set of slides. I just couldn't fit it in otherwise. If you're making a system-specific error code, there is a make error code, stood make error code function, and it takes a stood rc, whatever. This is one of the domains. There's 4 of them. You're never going to use the other 3, I think, probably in most realistic world code. You're going to use stood rc for almost all of it. And stood rc basically is the POSIX error codes. So they are generic, they're POSIX-y, portable. And they'll carry you 95% of the way most of the time. If you want to compare a system-specific error code to an error condition, and I'll just wait for this wee box to go away, what you do is you simply compare the error code, EC, straight away to the error code not enough memory. And the semantic mapping that's underneath the bonnet will go off, and it will fetch and run a runtime routine that will compare whatever your system-specific error code is with the generic one, and that will just work. So if you do switch statements, don't do that. Do this instead, just do direct comparisons, and it all works very nicely. You'll find then if you plug in ACCU, the networking TS, that just all works too, because it uses exactly the same framework, which is very handy. So part 2 of what's really clever about system error is that it was designed specifically to let you wrap up external C libraries. So you have some legacy C code base with some random error code domain, and without having to recompile it or modify it or change it in any way, you can wrap up its error code domain externally using system error, and it will now participate in the C++ type system with no recompilation at all. And that's huge, and nobody does it, and it's there in the standard. I mean, you look at code that's been written in the last 2-3 years, and you can see people going off with big switch statements, you know, to map such a third-party library. It's a new one, and you're kind of going, no. You should be doing this in the proper standard C++11. It's C++11 code, so why aren't you doing this, the standard library way? Now, the other thing is that since Visual Studio 2015 onwards, Stefan Lauwe has fixed a long-standing problem where the system error code category on Visual Studio did not map to get last error. As he says, it was a terrible oversight and he really wished he fixed it sooner, but it's done now. So if you're on Visual Studio 2015 or later, this stuff all works as the standard says it should work. Prior to that, you were getting inconsistent behavior, shall we say. Point is that you don't have to think about it. If you're on POSIX and you're dealing with error no stuff, it all just works. It's built into the box in C++11. And if you're on Win32, it's already built into the box if you're on 2015 or later. So lastly, I mentioned there before that NoExcept was controversial in terms of what it means. So what the standard says it means is that calling a function will never throw an exception, right? That's what is said in the standard text. But what does it actually mean? And I'm going to ask people in a minute. So, who thinks that the function can never return an error? Who thinks that? Nobody feels that it means that? How interesting. I had a really long debate with a senior Boost developer who said that it does. That if you put NoExcept on a function, you are publicly advertising that this thing will never, ever encounter an error condition. And that is a senior person with a lot of experience, and I entirely respect their opinion, even though they're wrong. That's why I'm not mentioning them by name. But genuinely, they believed it. So, do you think that it means that the optimizer can assume that calling this function can only exit through normal return? Who thinks that? Oh, I'd say about half the room.
Should mean that.
You're saying it should mean that?
Yes, question does mean it or should mean it.
Question is whether it does mean it or should mean it. That is a very interesting compiler vendor specific question. Okay, so here's another one. Does it mean that this function calls stood unexpected? Who thinks that? Guy thinks that. Does anybody else think that?
You mean always?
That would depend on the function. Does anyone think that it could call that? Yes, 2, 3, 4, 5. Ooh, there's quite a few. Okay. Here's the next one. Do you think that this function could call stood terminate? Now, who thinks that? Oh, I'd say we've got more than half the room again. Okay, so here's the answers. Maybe, yes, no. It will never, ever call stood unexpected. You're guaranteed it never will. And maybe. It's really interesting that it never call stood unexpected. It's actually there. And why it's there, I don't know. But if you throw an unexpected exception within anything that in the call chain has a NoExcept modifier, it calls stood terminate. It will never call stood unexpected, which I think is a surprise to a lot of people. That's not what you think is actually going to happen. And of course, it may well call stood terminate. A lot of people write code with NoExcept written on the front of it. And the code clearly can throw an exception because it calls into STL, and yet they've not wrapped it with the try-catch handler. So what they're saying, and this is unfortunately, the programmer should really have to explicitly write this, is that I want to terminate the program if this thing randomly fails, is what they should be forced to type out, that I explicitly am calling terminate. Unfortunately, the compiler just does this silently, and none of the recent compilers even warn you that you're doing it. You have to use clang tidy to get it to give you some warnings, and I think Microsoft's compiler on the really, really, really verbose warnings level, the one that spews pages and pages of completely irrelevant stuff, I think it warns there too. And it's the only two places that you're ever going to get a warning. It's really unfortunate. I really wish modern compilers would warn every single time that somebody fails to put a try-catch, unless there's some explicit opt-out. So, as we've seen beforehand, here is an implementation of OpenFile, but this time using C++ error codes. And anyone familiar with networking TS or file system library will be very familiar with this pattern. So I've not bothered telling you about struct handle. It looks really similar to the one before. There is, again, some smart handle, smart pointer reference. It's very same as before. Here is, firstly, a non-throwing overload. So what you'll see here is that we're opening a path. Here's your path. But now we've got this new parameter called stood error code with the L value reference to EC. I don't know why it always goes at the end. Somebody in Boost obviously decided that the convention should be that error code should go at the end of the function. I personally would have put it at the front of the function because I think it's an output, but that's one of those debates that you can go on for years and years and years and you'll never get anywhere except people shouting at each other. So there's no point in really discussing that. Once again, we do fd equals open the path with read only. If fd fails, so fail to open it, we now construct an error code using the error no, which is the error code returned by open, so it sets error no to whatever the failure reason was, and we specify std system category because that's the error code domain for error no coming from that on POSIX. We then return an empty constructed smart pointer. So what will happen when you call this is that the smart pointer returned will be null and EC will be set to the cause of your error. If you got past the opening of the file, you now try to allocate some new memory, and we're using std no throw to make sure that we don't throw an exception if we fail. And if it would just get its thing out of the way, as you can see, we're allocating down here some derived handle implementation. Interestingly, we have to pass in the error EC as well, because maybe this will set some form of error code during its construction. If the allocation of the memory fails, which is up here at the top, we now must close the file descriptor. We now must construct an error code matching eNoMem in C++11, which is done using this, std make error code, std error C, not enough memory. And that is now converted into whatever the platform local equivalent is for eNoMem, on whatever it is on Windows, I don't know actually. And you again return a null pointer. If there was an error anywhere in this earlier bit at all, we have to delete the memory we allocated because maybe the constructor failed for some reason. And once again, we have to return a null pointer. And if everything succeeded, we construct a new reference to the thing that we just created. Does that all make sense? It's a little convoluted, and is not the code that you would actually write in practice because it's used for exposition to make things easier for a crowd to understand. But hopefully that makes sense. Now, here's the whole picture, and this is one of those things where I really wish I could. This is the original text size, by the way, and I know none of you can read it. It's exactly the code that we just walked through. But there was a bug that was in that code. Does anybody know where the bug was? I shall just rewind back up. Does anybody see where there's a bug? Do you all think this slide's fine? Sorry, I hear lots of voices. No, because it's got a no-throw modifier on it, so it can't throw. Anybody else?
What is the initial value of EC?
Yes. What is the initial value of EC? The funny thing is, it's so easy to forget to go and do this, to remember that I wrote this code out, and I've been doing this for years, and I forgot to put EC clear into the front of the thing. And this is kind of important. Come on, where are you? Yes, anyone see a bug in this code? You need an EC clear at the top, because otherwise, if code calling this code happened to come along and there was an error condition, and as a result of the error condition, they happened to need to open a file, and they happened to pass through the EC, if it already had an error, the error would then appear to be returned by the open file if you didn't clear it. And this is something I wrote this code out, and I did these slides about 2 months ago, and I went through them however many times, and I never ever saw that the EC clear was there until 2 days ago. And the reason why this is really important is because it leads into the next section. Oh, just yes, before I move on, this is where I had one of those unfortunate things I did at 1 o'clock in the morning last night when I was making all the text bigger. This is important to emphasize as well for a second section, is that convention is that you provide a throwing overload for each of your non-throwing functions. And they generally take this form where you construct an EC, you call the non-throwing overload, and if there was an error condition returned, you simply wrap it up in a system error, and you kick it back out. Azure does this, file system does this, almost any library that's using this pattern does this. So I just wanted to mention that because, of course, what it means is that you get 2 API overloads for every single API that you have in your system, which some might say is non-ideal. As a use case, just in case, I think everybody seems to have got it, judging by your faces. You call your open file with an EC, you check, is EC the case? If it is true, you handle the error. So that all seems straightforward. Does anyone have any questions? All cool? Okay, cool. All right, let's see what the time is like so far. we're doing okay. All right, now we're getting into the new stuff. So I put a question mark after the C++20 because obviously it's not 2020 yet, so we don't know what's going to happen between now and then. I can guarantee you these will not be in C++17, that's for sure, but they could get in for 20. It all depends on committee time and a series of factors and whether this thing passes boost peer review, whether you guys all love it and go out and use it in your own code, or you all hate it and you immediately say, you know, on Reddit that this thing needs to be destroyed at all possible costs. That's fine, by the way. It's not my design, so that's okay. But all of these things come in. But let's say that there's a good, reasonable chance it might make it for 20. I understand from senior members of the committee that there is a generally positive view towards the expected proposal, caveated with a number of worries about niggly points, which I entirely agree with. I sent a defect list to Vicente of 15 different defects, which I felt were in the standard, but they're all very small corner case stuff that you would never normally encounter. It's only when you've implemented one do you spot the problems. So earlier on, you might remember that I had pointed out I forgot the EC clear in my own code. I also mentioned that there was 2 API overloads for every single public API in the library. And this is kind of where we're getting into where we could improve on what's in C++11. So this is why do we need a 4th way? Because this has come up, and I'm sure during the boost peer review it will come up again, because nobody will watch this video. Anyone who is watching this video, by the way, I didn't say that. But yeah, it's clunky. That's the trouble with the C++11 approach. When you're writing the code a lot, you find yourself having to declare a std error code. You have to make sure the thing's ready to go, and you have to pass it into stuff. You have to make sure you check it. It's clunky, it's unnatural to use. You just shouldn't have to worry about any of that. One of the big advantages of C++ exceptions is that you just get on with the coding, and if it throws an exception, you deal with it, but you don't actually have to manually walk out all of the code. So if we could get that stuff to go away, that would be really great, and indeed, this is what the proposal will do. As I mentioned before, having a throwing and non-throwing overload doubles your public API count. Some people don't see that this is a problem, but if you imagine a large library of 100,000 plus lines, and you look at the Doxgen-generated documentation, and that public API list is twice as long as it was before, just because you have to overload on EC, on the error code every single time. People look at it and go, oh, it's too complicated, I can't wrap my head around it. And there is a cognitive overload problem there. Doubling your API count for no real good reason is creating inconvenience and hassle for your library users. And if we could make it go away, that would be very handy. As we noticed before, error code is remarkably easy to get wrong when you're writing code with it. So the biggest problem, and I've done this, and I've been writing this stuff for years, and Chris Kohoff for ASIO has also been doing this for years, and it's really, really easy to forget to check EC after a function returns. The compiler won't warn you. It won't tell you the fact that you haven't done it, because it's returned by an L-value reference, so why would it? There's no way of it knowing any better. And you end up just not checking errors. So as a result, your error handling, you have no error handling because you've simply skipped checking for it. It's really easy to forget to clear EC on entry to a function. It happens so often, and then you find these weird bugs that pop out when your users are using it. They're saying, oh, it failed in this random case, and of course you haven't written a unit test to cover it. So it's another thing that if it just didn't do that in the first place, it'd be really great. And you know the weird thing is, I've been writing C now, 25 years plus, or assembler a bit longer than that. And you get into a use pattern with C that you always check the error code after calling a function. And when you look at the C code function, you remember check the error code. The trouble with C++ is that's just not ingrained into your head because you're used to using C++ exceptions. And in truth, you keep not checking for the error code far more frequently in C++ than you do in C. And I don't know if that's the same with all programmers. Maybe it's just me and my inability. But I've noticed that I make a lot of unenforced errors frequently with this stuff. So this is one of the motivations why I moved on something better. So obviously, C++ has some competition. Swift and Rust are coming along real quick and making C++ look terrible, according to the people behind Swift and Rust. And there is a perception, perhaps, that C++ needs to compete and be modern and cool with monadic stuff, same way as Swift and Rust do, because Swift and Rust both use these monadic transports for their main error handling system. And that's the error handling system that they have. Although Rust recently, interestingly, effectively has just implemented exception throws, except they're always fatal. But that's a separate issue. It's politics. There's the last thing, which is kind of one of those funny things which only comes up if you're a library programmer or you really, really love metaprogramming. And that is that error code was designed in a day before constexpr. And because it was designed before constexpr, it cannot be used as constexpr because it uses a singleton, and the singleton is created at runtime, so therefore there's no way of creating an error code as constexpr. And you might wonder to yourself, why would I ever need to have error handling in constexpr code? Well, you can throw an exception, but that creates a compile error. And sometimes you don't want a compile error, you actually want an error code passed through your constexpr code, so code at the bottom running in the compiler's memory has realized that an error has happened higher up in the compiler's memory and do something about it. That's one use case. Another use case is that if your constexpr code is called in a non-constexpr evaluation context, it will be run at runtime. And in this case, you do want error handling to be running. So it's one of those things that, because stood error code is unsuitable for that use pattern, if you had something that could be used for error handling in constexpr code, this would be really handy. You can then transport errors in constexpr or not, or whatever else. So this is where the library evolution working group came up with this proposal called expected. And I tried to make the T green and the E red for illustrative purposes. I think I've got it through all of it. But it's very, very similar to what Swift and Rust do. There's very little surprise here. However, obviously, because we're in C++, we need to get this proposed expected class to fit in between what's currently going on inside the STL. And by the way, this is slightly controversial. I was talking to Marshall Clow yesterday, and he was saying, well, I don't really like stood variant. I think stood variant should not be the way it has been standardized, and as a result, he's aiming to get that fixed. So it could change in a future standard. But for now, let's just assume that stood variant is stood variant and stood optional, and they're done. So stood expected, kind of sitting in between the two of them, because stood expected can store either a T or an E, so it's like a variant in that sense, but it's got the same API as an optional. So it can slot in where an optional is, because optional can be a T or nothing, and expected, and I'm going to get in trouble with whoever's watching the video for this, an expected can be nothing, even though it's never supposed to be nothing, but we'll get onto that later, a T or an E. So it is similar to an optional in that sense. I'm just interested, there's in quotes here a never empty guarantee. Does anybody know what that means? Why it's in quotes? Would anyone like to say?
It's not empty unless you get an exception at the right time.
It's not empty unless you get an exception at the right time. Is that what you're going to say, Anthony? Yes. And that is correct answer, yes. So the great trouble with stood variant is that sometimes you're in a really awkward position where you've just destroyed one state and the process of making a new state throws an exception. So what do you leave the variant in what situation do you do? And after 8-9 months of committee argumentation, they eventually came up with this idea of an empty state that we will not call an empty state, and we will try to pretend doesn't exist. We're going to claim the thing is never empty, even though it has an empty state. So this is why I put it in quotes, is because it's a never empty guarantee. And I think it's the least worst choice out of all of the choices that were available. The other alternative is to have memory allocation happen every single time that you use the stood variant, and that would just be pointless. I mean, we have a thing in Boost that does it already, and there's no point. So the greenness of the T, the reason why is because that's an expected thing. It's a positive thing. It has been denoted as being, yes, it's the thing that should be the case most of the time. And E is in red because it's an unexpected thing and should be not expected. Now, an earlier proposal for expected did lots of really cool semantics with that assumption and did lots of funky monadic programming. All that's been stripped away. It's gone out of the standard. Not even being proposed at the minute. So all you have is expected or unexpected, and that's it. There's no particular fun that comes out of it as a result. Okay, so this is the exposition of the synopsis of the expected class. So you're now looking at training, almost. This has been split over 2 slides. It originally fitted onto one because it's such a simple proposal in its current form that it actually fits onto a single slide. So, and I'm using the latest paper before Library Evolution Working Group at the minute, so it's the very latest one. So there's a class T. E is being defaulted to the stood error condition. Pardon me. All of the same member functions from optional follow after this. So I didn't bother spelling out every single constructor that expected has, just assume that they're the normal ones. There's an indirection operator, there's a star, there's an explicit operator bool for testing if it's an expected value state or not, and there's a has value, which is the same as optional has. This is a defect in my opinion. It shouldn't be error condition. If you remember earlier on, I said that error condition is for semantic mapping of error codes. It is not a transport. Unfortunately, it permits transport, and this is why the mistake has come in. So I've reported this. It took a few days of explaining, but I think I've got the message through, and I think it will turn into a stood error code soon. That's literally happened this morning. I had an email, and I think I've got buy-in to that argument. And if you go back actually to Chris Kohlhoff's blog from back in 2005, 2004, it becomes really, really clear why it should be stood error code and never error condition. It's a shame that the cpvreference.com documentation needs to be upgraded actually to fix this, but we'll get to that. Up here, there's a const expr value member accessor, and there is a value or. So if there's a value in the thing, you get back t. If there is not a value in the thing, you get back a u. So that's just a simple little bit of magic, I guess. Here's the additions to stood optional. So you now have a new error type, which is set to E. You have a new implicit constructor, which takes unexpected type E, which is type sugar for constructing an E. So the default for expected is that if you feed it to T, implicitly it will convert into an expected. Obviously, you can't allow that for E, because E could be the same type as T. So for example, in the LEWG expected test suite, there's a whole load of expected int, where int can be the error unexpected state, and int can also be the expected state, which is slightly confusing, but that's okay. If you want the second unexpected int, you wrap it in an unexpected type, and that's the way you get around that. And then you can access the error, if there is an error, using this. So that works as well. If you try to access the error when it is a valued state, you get an exception thrown. If you try to access the valued state when there's an error in there, you get an exception thrown. And then, of course, if it's valueless due to exception, you get another exception thrown. So it's a very standard, it looks exactly the same as anything else in the STL. So down here is an interesting one. These are the make standard things that you get in any STL thing. You have a make something of whatever you want to make. You notice here that it takes a R value reference, or what they used to call universal references, and we're no longer allowed to call them that because apparently that's bold. And down here we have a make unexpected as well. So here's another interesting thing. I think these are a defect too. And the reason why I think these are a defect is because you can't do make expect const foo, right? So your type t, if you want it to be a const t, you can't use make expected with the current proposal to do that because the decay will take out the constness. Now, it's kind of interesting because why would you want a expected const t? And it actually turns out to be quite useful to be able, in real world, at least in the code I've written, to preserve constness sometimes. If you're writing generic code, you want the constness not to be stripped out if it really, really is a const thing. I mean, if you do want to, then you explicitly say, I want the constness to be stripped out. And the trouble with the decay here is that no matter what you do, even if you manually specify it, it's still going to get stripped. So you're going to get a expected foo, even though you asked for a make expected const foo. So I think that's a defect personally. And I might have got buy-in on that. The trouble is the current LEWG expected reference implementation can't cope with const t members, but that's okay, it can be retrofitted to do it. And the boost outcome implementation can, so that's fine. So I'm going to deliberately not mention monads very much at all in this talk because, as I say, people get really scared away by them and confused. But if you are into your monadic programming, all optional is a maybe monad, and the either monad is an expected t. So that's what C++ is intending to do. And these are really, really simple primitives. Nobody's expecting this to be a really massive, full fat thing yet. Maybe a future standard will have it. As I say, they're broken out the monadic programming API into a separate proposal. The reason why is because a future is also a monad. It could be used for an IO monad and a long list of other things. So if you have a standardized monadic framework, you can bring in all of these parts of the STL that behave a little like a monad and actually make them into a full monad. So that's why that's been pushed and kicked down the line. That will happen way after C++20, I would imagine, because there's lots and lots of fun. In case you do want to get on with a proper monad programming in C++, Outcome provides its own monadic operators API. You have to turn it on using a macro, because if I have it on by default, then Boost Peer Review will review it and will slam it terribly because it's really impure. So it's turned off by default, but you can turn it on with a macro and have lots of fun. It's not going to be part of the Boost peer review because I don't want feedback on that code. And you might see why if we get a chance later on. So this is a bit that I'm really sorry that it's on such a small screen. So any of you who have tried the Rust at any stage to give an investigation, you will have almost certainly come across its result type, because that's the main error handling system in Rust. So you'll have seen this lovely example on the Rust documentation webpage, which is a terrible, terrible example of how not to use ResultTE, but hey, it's the documented example. And because people like to correlate stuff from Rust onto C++, I have converted that example into the same code written using expected, so you can see them left, right. So this is the path to the Rust example. None of this will really matter to you very much if you've never done Rust before and don't care. But it might sort of illustrate maybe as, you know, you shouldn't do the code pattern that's in here because it's wrong, it's badly designed. But it is illustrative, so we'll see what happens. It's unfortunately quite long, but anyway. So here we have namespace checked because that's what Rust used. Here are the mathematical errors that we want to catch. So this is going to be our error code domain, and you might notice it's a strongly typed enum. So this math error can be division by 0, negative logarithm, or a negative square root. And what we do down here is we type def the expected, taking a double as being the expected value, and math error as being the unexpected potential value, and we put them into an expected and we map them into math result. And the reason we chose math result is because that's exactly what the Rust example uses. Does that make sense so far? Okay. So for some weird reason, this example uses the potential for floating point operations to have errors come out of them as a rationale for writing this code. As I say, you would never ever write this. Well, if you do, you probably are a Rust programmer. That's a mean, mean thing to say. I had a contract a while back, 6 months of writing Rust, where I'd learned it for the first time, and I saw some terrible, terrible code written in Rust due to lack of experience. Anyway, here's your div function, and it returns the expected that we had earlier on as a math result, and it takes in a double x and a double y. And you might notice it's NoException, so this thing can never ever throw exceptions. So in here, what we do is we take the FABS of y, and if it's less than float epsilon, which, does anybody not know what the float epsilon macro is? You've all seen it before? Oh, you're very skilled, very skilled. Excellent. So float epsilon, for anyone who's watching the video, is the smallest value near 1, which can be represented in a double. I think, am I correct in that? Yeah, the smallest increment, is that right, off 1?
Yeah, but that's the point.
Yes, it is, that's a bug. Yes, 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 Roger. Yes, 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 that's a bug. Yeah, okay. I have to go fix that. So let's just assume that these are floats, and that's an FABSF, and this would now make sense. Ah, dear, dear, dear. Do you know the weird thing is that how many people have reviewed this in the documentation for outcome, and nobody has yet raised that? So we live and we learn. Excellent. So anyway, if it is less than ABS, because down here, if you were lower than float epsilon, which is a really, really, really minusculely tiny number, and the next value down below it would be 0. So here you're trying to avoid a divide by 0 exception. So what you're doing is you're testing for this to be lower than that, and if it is, we return the error code of division by 0. If y happened to be just over 0, then we divide x by y, and that comes out because there's an implicit conversion into the expected value out of math result. Is that all okay? Okay. So here we have square root, and once again, we don't want to square root anything which is less than 0, because square rooting something less than 0 might be bad. So what we do here is we see if it's less than 0, and if it is, we return the error code negative square root. If, on the other hand, it was not less than 0, we return the square root. Yeah, cool. Here's your logarithms. Once again, if the value being logged is less than 0, we say negative logarithm. Otherwise, we execute the log. All pretty straightforward? Cool. So now we're going to combine them together. Here's an op, and the op will call divide. And if the returned value from the ratio is evaluates the Boolean false, that means it failed. Then you print panic, because that's what Rust does. And you say division by 0, and you call terminate, because that's what Rust does. So, panic, division by 0, we can't cope anymore, stop the program. Similarly, down here, if the log failed, we have 0, and we say negative logarithm, we call terminate. And once again, up here at the square root, we have exactly the same thing as we had before. So you might have noticed there that we've been feeding the values from one into the other. So you notice here that the ratio gets fed into the ln. So what we do is we use the star operator to dereference it. I personally really hate that design choice, but it's instant optional. So once it's instant optional, it's there, it's done. I personally think that's an abomination, but ship has sailed. So there we go. And down here, again, we feed the result from ln if it was positive, and that goes into square root, and then it comes out. And then at the very end, you access the value from the square root by returning value. And if you might remember, back up. And you might remember that op returns double. So it is using expected internally, but isn't exposing the fact that it's using it externally. And down here, simply because the Rust example said in a comment, will this fail? And you write that down, and that's there. It doesn't actually matter if it fails or not. I don't care. It's a terrible code example. Awful. It shouldn't be in documentation. But anyway, but you get the idea. Does anyone have any questions with this? Seems pretty easy. This stuff's really easy until later on when you're trying to use it. And it just all vanishes out of your head. So I'm going to do a second example, much better use case using the open file, same as we had before, so you can see the pattern. Okay. So now we have exactly the same handle as we had before, the exact same smart pointer managing stuff. I put expected into an experimental namespace, probably because that's where it's going to go live initially. And it has a positive return of handle ref, and it has a negative return of a std error code. I really wish there's indenting here, but here's your open file, and there's the path going in, and you're saying this thing will never, ever, ever throw an exception. Crappy. Go back here. So here you open the file. Once again, it's read-only. If it failed, you have to write this really long and involved piece of boilerplate, because unfortunately, you have little choice with the way that expected has been currently proposed. So you return your make unexpected. You then have to convert your error number into an error code with a system category, and as a result, you get this really long line. That then returns out as an unexpected outcome. Down here, you create your error code, and you call std new with std no throw, so never throws, and you're calling some derived handle implementation the same as we were in the last example of this. We're passing in the EC. Once again, if the memory failed to allocate, we close the file descriptor. We convert the portable error condition of not enough memory into an error code, which we then return using a make unexpected, and that then wraps out and fires out the return. And then if the derived handle implementation failed, we move the error code that was returned by the constructor into, again, a make unexpected. And finally, because of the implicit construction, it returns out the handle that way. Is that all okay by everybody? Once you get used to writing this stuff, it becomes really natural. The only thing is, when you're at a boundary between expected land and C++ throwing exceptions land, you end up having to put .value at the end of everything. So all the stuff you're writing, because you're explicitly wanting the stuff to be re-thrown out as exceptions, it's .value at the end of everything. It kind of looks ugly. Question?
So why can't expected have an implicit conversion to the error type, so to avoid the make unexpected boilerplate?
So the question was, why can't expected have an implicit constructor to the error type so you can avoid the boilerplate? This is exactly what outcome does. This is the outcome extension. But the expected proposal, as is currently before the committee, currently what I'm told is that they actually want to remove the implicit constructor completely, and you'll now always have to write make expected or make unexpected. The reason why is because of comparison operators. So because of the implicit constructor unexpected, if you now use expected in an area like a hash map or an associative container, you get really, really unhelpful behavior, which is wrong. So the way that they're going to think you're working around it is to make it impossible to implicitly construct an expected at all. I say that's a stupid idea. I think you should just get rid of the relational operators. Why would you want to put an expected into a std map? If you are, I think you're doing the wrong thing, personally. But apparently LEWG does not feel this, so there we go. Anyway, Interestingly, outcome happens. The outcome refinement does not permit T to be the same type as E. And as a result, we can now offer implicit constructors for both. And there's a static assert at the beginning to say you just can't have the two to be convertible at all into one another. And it's much, much more easy to program. You don't have to write these big, long thingies. So yes, that's one of the little tiny changes. Okay, any other questions on this? All pretty straightforward? Cool, okay. Only an hour in. Here's a use case for the thing that we just had, so you can kind of see how it gets used. So here we've just simply called open file. I usually use auto for the return type because I don't want to type out expected with the type that's been returned that's positive and the type that's returned that's negative, because to be honest, it's none of my business. Whatever open file happens to say it's a return type, that's what auto's for. Auto should just take that and you don't need to think about it. That's not your problem. You now go down to here, so your testing is the thing returned, evaluating to Boolean false, in which case it has some sort of error in it, in which case you test the error, and you see, was it a no such file or directory? And if it is, then this is serious. We need to throw it as an exception. So what we do is we wrap the error code into a system error and we throw it. If, on the other hand, it was not, if it was a no such file or directory, so in other words, if it was that error code, we simply pass through because that's not being evaluated here. Down here, we test is it true? In other words, did it succeed? And if it did succeed, we move the value out of the returned from FH into a handler ref FH, and we call read or whatever else we want to call on it. So that's the use pattern. All okay with everyone? Okay, cool. Let's get another bit of water. I don't know why my throat, so I suppose I was up until 1 redoing all of the slides, and that's probably what's made me a little dehydrated. But I am unusually thirsty today. Okay. So here's the benchmark that I promised. One of the big things that's come up on a number of occasions is why do we need all of this extra stuff? A lot of people still believe that C++ exceptions are fine. If you don't need them, just use error codes, as in C integer error codes. So a lot of people don't realize just how slow exceptions have become on modern CPUs. So why not just throw exceptions and save all the hassle? I've heard this a number of times. So here's some numbers. I'm going to firstly caveat with something that anyone on SG14 study group for low latency knows. Benchmarking this stuff is hideously difficult to do something that's actually useful. One of the great troubles we had on SG14 when the discussions come up about whether exceptions are turning them on is bad for code performance or not is that proving it is exceptionally hard. The trouble is that if you take a synthetic benchmark, it's going to be too simple, and it's not going to have conclusive results. If you take an existing program and you convert it over to using error codes and you convert it over to using exceptions, you'll always find that because it was written to use one style to begin with, it's always going to go and put a bias on the way that it comes out. So what you really need to do is to write the same program, starting from the initial assumption of error codes, starting from the initial assumption of C++ exceptions, and that's basically doubling the work just to go and prove that C++ exceptions are a bad thing. And interestingly, I think there was a guy on SG14 who had done some of this and had found that there was virtually no performance difference for his particular application, which may not be, of course, what happens for other applications. So I'm simply caveating that all these benchmarks are totally up in the air and maybe they mean nothing or maybe they mean everything. Who's to say? This benchmark is extremely simple, and I deliberately kept it so. It is a worst case benchmark. So it is the absolute worst case performance that you could ever have, ever, and will never actually appear in any real world code. So the way that it works is really, really simple. I have a wee bit of Python, and what it does is it goes and generates multiple C files, or C++ files, as the case may be. And each file simply consists of one function. That one function calls the next function in the next C file onwards, and it does, it accesses a volatile int. It simply adds a number to it. The reason why we do a volatile int is we want to force the compiler to actually do some work for every single function that gets called. But all it's doing is it's incrementing a volatile int on entry, and it decrements it on exit due to the stack unwind. That's all it does, is the sole bit of work. And by the way, volatile int is not an atomic. It's just a normal, everyday thing. It's virtually no work, as little work as you could possibly have. So what you now do is you compile each of these 10 source code files individually into their own object files, and you go and link them. So they're all linked, and you don't turn on link time code optimization. You keep them all as separate things. They're all having to call into one another. They're not inlined or anything. In the call sequence, your 10th function either returns a value or an error. It doesn't actually matter which. We benchmarked both to see what would happen. And what we did was we iterate them 100,000 times to get some notion of average performance in all of this for many combinations of compilers. So that's it. It's a really, really simple benchmark, and it's a worst case because you're jumping between ABI boundaries every single time, so the compiler can do no optimization of any use to you. These functions are marked extern. It can't do any inlining. It can't do anything else. It just has to call them one after the other, and when you're unwinding them, it simply has to return back out through them. So the test hardware is that their MacBook Pro. I'm really weird that I run Windows on my MacBook. I never run OS X. I don't see any point because why would you bother? They have just done nothing with that operating system in about 7 years. But Windows 10, in fairness to them, they just keep incrementally improving it. And the Linux benchmarks, I'm going to caveat you right now, are not real Linux. They're actually the Windows subsystem for Linux, which is amazing because it lets you do a complete Linux work environment with the Windows kernel using the Windows file system on the same code base. And best of all, in Visual Studio 2017, they've now integrated GTP support such that you can now launch a complete compile and debug session on your fake Linux running on your Windows kernel via Visual Studio. So you're sitting there debugging in one, and you just simply flip over to your Windows and debug with exactly the same stuff because the file system is exposed identically in both systems because Windows can now run Linux programs. So it's fantastic. So the benchmarks aren't for real Linux, they're for Linux on the Windows kernel. And by the way, I did check on real hardware, they are correct. So I did check on the real Linux. Here's your Windows 10 version. I also tested on Apple macOS, which is I think the first time I booted into OS X in probably since I bought it. I had to install Xcode for it. Here's this CPU. It's a 3.1 gigahertz Skylake. It's got this much memory bandwidth and that much latency. Some people reading this on the video might care about that kind of stuff because that will obviously affect the results. This is mostly going to be a memory-bound operation because the CPU is going to be stalled on memory almost all of the time. It's doing no work, so you're just waiting around for memory. So this is one of the troubles with these really tiny slides. I couldn't readjust the graph to cope with this really long room with this really tiny screen, so I'm going to read out to you what this tiny little text says. So up at the top, it says cost of returning error ups 10 stack frames on x64. So you've got 10 files, 10 stack frames, and this is what it takes to go and return up each of those 10. Over here is total CPU cycles. So this is a CPU cycles thing, and it goes 1, 10, 100, 1,000, 10,000, 1 million. No. 100,000, can't even read my own stuff. Down here, this is GCC 6.2-NoExcept. So these benchmarks are for GCC with C++ exceptions disabled. Over here is GCC 6.2 in default settings. So now you have the bar clearly for, you can guess what that one is. Here you have GCC 6.2 with link time optimization turned on. So link time optimization can go across the object files, and it can say, well, these object files are just little tiny functions calling one another, so we're just going to inline them entirely, so you can see what happens with LTO. Over here is Clang 4.0, running also on Linux subsystem for Linux on fake Linux. Over here is Microsoft Visual Studio with no exceptions. This is with C++ exceptions disabled. Over here is with its default settings with, it's actually untrue, isn't it? Microsoft's compiler actually defaults to C++ exceptions disabled, interestingly, but they're turned on for this. And over here is where Microsoft's compiler does link time code generation, so where it has a chance to inline. And finally, over here is Xcode 8.2 running on Mac OS X. So that's what this bar over here is. And this is a log scale. The red bars are for integer error codes. This is C, so the standard C return code is the red bar. For the green, the light green one, this is for when expected is returning a value. So it's when it's returning a value, not an error. The dark green one, which hopefully you're able to see, is for when expected is returning an error state rather than a value. And then here your lovely, lovely yellow bars are for when you throw a C++ exception. So to give you an idea, that's about 30,000 CPU cycles to throw and catch a C++ exception over 10 stack frames. This is 100 cycles to return an integer error code, or as you might notice, expected is extremely close to integer error codes. There's virtually no overhead all the way over here. The C++ exception throw and catch is unbelievably expensive on modern CPUs. You might wonder yourself, why is it 30,000 cycles? So I dropped a wee email to some compiler vendors I know, and they think it's because of the RTTI lookup. So because you're going across an ABI boundary, the compiler can't do any deduction about the types being compared, and it has to do an RTT lookup. And because it's doing an RTT lookup, it's doing one for every single stack frame it's unwinding, and as a result, it goes real slow. This, by the way, interestingly, is linear. So the scalability of exception throw and catch is linear to the stack frames being unwound. So if you unwind 10 stack frames, it's 30,000 cycles. If you unwind 100 stack frames, it's 300,000 cycles. It literally goes up, straight line. So stack frames, by the way, can be any destructor, any single unit that has to be unwound. If you think about any modern C++ code base, there's probably dozens and dozens of things which are unwound when you unwind a stack. The cost of an exception throw just goes up proportionally. The bigger and bigger and bigger those get. It just gets more and more and more and more and more expensive. So this is food for thought. When I posted this to SG14, people were like, ooh, wow, that's really interesting. I decided to remove the yellow bar to get rid of the log scale so you can see for yourselves without having to look at the exception throws messing up the values. So you'll notice over here exactly the same graph as before. So the red line is integer error codes. You'll see here that on GCC with exceptions disabled, they're the fastest. Expected with a value is slightly slower, and expected with an error is slightly slower again. But we're talking here 1 CPU cycle or 2 CPU cycles. I think we can probably live with the added overhead. I don't know, maybe some people here would go, no, 2 CPU cycles is too much. I don't know. But if you do think that, GCC with exceptions enabled, interestingly, the expected value return is slightly faster than C integer error codes by, again, 1 or 2 little cycles. Why this is the case, I don't know. It could just be statistical measuring noise. In fact, I almost certainly think it probably is. Sorry?
You did it enough times, you must have some idea of what the noise is.
I think for when you're getting down to 1 or 2 CPU cycles.
No, yes, but you did, these are averaged over 100,000 runs.
They are.
So you must have some idea of the distribution. Yes?
No, because I wasn't measuring per stack frame, because it's such a small operation that to do the measurement there would affect the results. So I literally start the timer, I run this thing 100,000 times, I stop the timer. So it's completely averaged. If you do it per stack frame, the measuring of the timestamp counter actually affects the results. You know.
I misunderstood what you've done. I thought you'd run it for a long period, 100,000 times.
Oh, so the point was I'd run it for a long period over 100,000 times. No.
You don't get any statistics if you don't do that.
No, the point was that you don't get any statistics if you don't do that. You're absolutely correct. I think that you could do a really involved study into this and come up with interesting stuff, but how relevant it would be to real-world code, I don't know. It's very toy, very abstract. I think it's good for getting compiler vendors to think about stuff, because it kind of makes them all go, huh, and we've achieved our goal with that, you know. But I agree, these could be statistical noise. The point I'm trying to make, though, is that expected is virtually the same, and you're within 10% value right across all these compilers and all these systems of returning C integer error codes. You are paying no, I'm going to say nearly no, runtime overhead for using the type-safe expected rather than using C integer error codes. So have I convinced you that these things can actually be used instead of C integer error codes? Is anyone feeling they can't? Cool, so I've achieved something. Because some people say, well, these things must be slower. But they're not. Not at runtime. They're slower for the compiler to compile, but they're not at runtime. The overhead is statistically, I think, if you're going to go do a test, is the case. Now, I will say that constructing an error code is slightly more work than not constructing an error code, because you have to go off and you have to go fetch the singleton, and you are doing an extra memory access there. So that's your extra overhead over doing a C integer thing. It's tiny, minuscule, except on Dinkumware STL. The reason why is Dinkumware STL uses an atomic fence anytime you go and collect an error category. I have mentioned this to Stefan, and he says, well, that's because that's what the standard says. But I said, but libc++ doesn't do it, and libstd C++ doesn't do it. I mean, none of the other STLs do it. They said, well, they're wrong. So go figure from that. Now, even if it's an atomic fence, it's not the end of the world. I have some stuff in outcome that caches the result that comes out of the atomic fence. You're not actually running the atomic fence if you're using the outcome implementation of expected. So I guess go figure that. Any questions about that graph? At the back.
Could you comment on that, the exceptions occur when something was wrong, but although the expense in doing error codes
So the point was that the cost of doing errors is a permanent cost, whether you're...
Yeah, doesn't it exist always, even when things are working correctly?
So the point was that the cost of the error handling is existing always, whether you make use of it or not. I think that's correct, yeah? It's a permanent overhead, yeah? Yeah. I had that argument made to me by a number of finance firms who brought me on as an expert consultant, because I work for an hourly rate for whoever comes and pays me money to go look at problems. And I've heard that argument made by finance firms, high-frequency trading firms a lot. My view on that is that a fixed overhead is correct, a fixed overhead, but it is fixed. So you can, if you really, really care about it, you can if-def it throughout the entire code base, such as if-deffed out, if you really, really care that much. I would say that as a fixed overhead that is non-scaling to load or to time or anything else like that, it's something that is very worth considering to pay because it doesn't cost you anything other than the fixed overhead. So it's not a variable overhead. You know, if you have twice as many packets coming in, you're paying a fixed amount for that, not anything more. So I agree, there is a point. I mean, if you're really super duper duper keen about absolute minimum latency, then you should have no error handling. And of course, that's what quite a few high-frequency finance traders do. I often find that they do a whole lot of other stuff, which makes things go slow, and I don't think error handling is actually anything like the overhead they think it is. But that's a personal opinion, and in the end, the client's always right. So, any other questions? In the middle?
On the expected class, the value access function, is that overloaded for reference qualifiers so you can get a reference out?
So the question is are the value and error member access functions overloaded for R value reference and so on and so forth? The answer is that in the LEWG expected proposal, the expected member values are overloaded. The exception thrown type is missing them, but is shortly to be added to them because that was accepted as a defect. And in the outcomes implementation of them, there are R value and L value const member overloads for all of them. So it does the right thing. So if you stood move from it, it will stood move. Any other questions? At the back, Phil.
Is there any facility for chaining these calls together? So you can work within the aerospace without getting very...
Sorry, you're going to say that again?
So you have your sequence of operations where an error might occur, and then you do the checking, and then you dereference it and feed that onto the next operation.
Correct.
But you could compose a series of lambdas together where the error handling is actually off to the side.
So the point was that instead of manually checking this stuff in good old-fashioned C style, you could compose a set of lambdas that would put the error checking off to the side. You are now straight on to outcome extensions, literally. So I have that covered. It's not, again, in the standard proposal because they've left that off until they kick the can down the road. But yes, that's exactly what the extensions do. There was another question. Oh, yes?
Is there any guideline about using this in the context of constructors, like the constructor needs to return error as used to throw as always, or someone it's a static method and return is expected? Is there any thought given to this or any guideline?
So the question is there any guideline for using these constructors? Because there's no way of returning a value out of a constructor. And the answer is that you are just as hobbled with constructors not being able to return values with expected as you are with integer return codes or error codes and anything else. So what you do in practice, and certainly my code, is you have a static initialization function which does return one of these, and then you make sure that your constructor can never ever return an error or fail. And then what you do is you basically construct const expr and you fill in the stuff afterwards, just like you do in Qt or any of the other things going right back in the day. It's a C++ limitation, unfortunately. I have been thinking about some funky ways of throwing exceptions and catching them up as a way of working around the C++ language implementation, but then I slapped myself and said no. So, because it's just so rife with corner cases and misbehaviors, just don't do it. There was a question here, yes.
Is there any room to actually get error category working with const expert? Anything you can do about it, or is it basically just burnt in there?
So the question is there any way of getting error code to work with const expr? Or is it burnt in? Without breaking backwards compatibility, the ship has sailed, I'm afraid to say. There has been an argumentation for an error code 2, which remedies some of the mistakes that error code had. And one of my biggest troubles I have found with error code in practice is it has no payload. So the only payload you can put into it is an integer error code or a reference to a generic category. In practice, when you're using these things in the real world, you really want a void pointer. You really, really, really want a void pointer in there. Just some extra little bit of storage to put in. And outcome happens to come with one such thing. It's going to be the most contentious part of the Boost peer review because I use a static piece of memory that's allocated in nowhere land. And it's a ring buffer that gets filled. And we had to do this because we had to retain the trivial destructor on error codes. Otherwise, the code doesn't come out anything like it's nice in terms of assembler and overhead. So this thing lives in la-la land and will get deleted at some unknown point in the future according to when threads come along and happen to recycle the storage. And this will be a problem in the Boost peer review because people are saying, what do you mean the storage will just magically vanish at any random time? And that's okay. If they do have that problem, I might add that the storage is completely pod. It's all plain old data, so you can whip it out from underneath while another thread is running. The only thing you're going to get is a Clang thread sanitizer warning. But I have a feeling that the Boost peer review is going to say no to that, and they're going to insist I put some sort of locking in there, in which case that's fine. So some sort of locking will go in and prevent torn data being ripped out from underneath a thread access. Is there any other questions? There's one just here, yeah.
So while using these, shall I think about corner cases like it's an unexpected state, but error code is in a clean state, or expected state, but my pencil or pointer is now check those.
The question is when you're using expected, should you consider the corner case states of the different combinations of whether, for example, a handle is invalid, whereas the expected is valid, or expected is invalid and handle is valid, and long list of things like that? The answer is if you don't want it to throw exceptions, if you're writing all no throwing exception code, then yes, you do. You need to cover all of the corner cases. Outcome, by the way, works with C++ exceptions disabled, but its default behavior is to call a macro whose default implementation is to call std abort after printing a stack backtrace. So if you ever get into a situation where an exception would be thrown, it kills the process. Now, you can override that and do something else, but the point is that you need to not put the program state into an unrecoverable situation, because if you do, what else can you do? You have to kick out. So does that answer your question?
I'm mostly worried about this case when let's say for some reason I will make unexpected with an error code, which is a clean error code. So it is unexpected, but error code, no errors.
So the question was, can you not make an expected in an unexpected state with a clean null error code? Yes, you can. And there might be an actual use case of that in your code. You might overload that with special semantic. That's up to you. That's the programmer. The standard and the proposal says nothing about what bad ideas you might put these things to. It's the same way as you can do all sorts of silly things with the std vector. The standard doesn't say what you should or should not do. Okay, we'll have to move on because we've only got about 10 minutes left. That's all right. There's more questions at the end, and indeed, you all can be asking questions using the link at the top, if that's working. I don't know. One of the big questions I always get asked is, which error handling system should I use? So I'm going to simply equivocate and say it entirely depends on your code. I've had people ask me, well, should I write everything using expected? No, you shouldn't. Should I write everything using C++ exceptions? No, you shouldn't. You should write whatever combination of error handling systems is appropriate for your particular code base. And by the way, one part of a library might use expected, a different part of the library might use C++ exceptions, and a different part of the library, again, might use std error code directly. It all depends on the design of your code, the particular factors that are there. It's the skill of the programmer in deciding what's the best design for your particular code. And I might add that throwing exceptions all the time can sometimes really make sense. 30,000 cycles is nothing compared against a 10 microsecond operation. Sorry, 10 millisecond operation. So one of the classic ones, I'm very keen on writing a embedded database architecture framework. So you have basically a set of core algorithms for the file system. You might have seen me in previous talks about this. For C++, so it's just built into the standard library where you just have this toolkit of elementary file system algorithms. And the idea is that you would have a situation where you're trying to do a transaction, and you get to a point where you have a conflict with another writer, and in that situation, throwing an exception and aborting and unwinding the stack is really the right thing to do, because the cost of a filing system operation is so much more than any exception throw will ever be. It's the right thing to do. It's the ideal way of doing it. So sometimes throwing exception code, throwing exceptions is really the right thing to do, even as a form of control flow. It's very rare, and you shouldn't do it, but occasionally, in some code bases, it's the right thing. So that's my argument on that. So with 10 minutes to spare, I'm going to try and quickly kick through proposed boost outcome, so you have some notion of what's coming in, and I'm glad that I spent an hour and, whatever it is, on nothing but expected. This is great. So last time I was in Seattle, I got my timing completely wrong, so this time it worked out really, really well. I don't really want to harp on about this until it comes to peer review at the end of May, but what I will say about it is that it is a higher quality implementation of the LEWG proposal than the LEWG reference implementation. We're closer to the proposal than they are currently with their reference. I would add that a huge quantity of time has gone into making a very, very compact assembler. Outcome began its life as an alternative to expected because of all of the deficiencies in expected many years ago. As a result, it's a really mature library that's been in production use for at least 2 years. It's had all those little tiny tweaks fixed, all those little corner cases have been ironed out. Huge quantity of time has been spent using this in real-world code and stepping through the assembler generator to make sure that the assembler generator is absolutely minimal. There is a test suite, which goes off and compiles canned examples of use cases of expected. Then there's a bit of Python that goes through and counts the assembler instructions to make sure they don't exceed a certain limit. And if they do for a certain commit, it will fail commit on continuous integration. That's the level of detail that is in this. It's a very mature library. It's been around for years. I only added an expected implementation in January, but it reuses all of the internal machinery. It was really quick to do. I simply instantiated the policy class. I said, you are now an expected implementation, and it just goes whoosh. And it passed the LEWG expected test suite first time. Just went whoosh straight through. So that's great. I might add that it works very well on all major C++ 14 compilers. You might notice I've written minimum, Clang 3.5, GCC 5, and Visual Studio 2015 Update 2. And I wrote a best, Clang 3.6, GCC 7, Visual Studio 2017. The reason why is that even though the outcome unit test suite will pass completely green on the minimum compilers, if you use it in real-world code, in real actual use cases, you'll find compiler bugs. So you'll find the compiler will internal compiler error, it will blow up, it will fail to compile, it just won't work right. But again, it depends on how you use it. Whereas Clang 3.6 I found to be pretty reliable. GCC 7, they fixed the bugs I sent in that outcome triggers. So it should be okay. And Visual Studio 2015 still has a raft of workarounds, but the compiler team have promised me that update 1 will fix all of the issues except for one of them, and then update 2 will fix the last remaining issue. And we can remove all of the Visual Studio specific workarounds entirely out. Until then, you don't need to care about it. You just get to use the code, and it should be fine. So I have some deviations from the expected proposal. Some of these are going to go away because I've won buy-in for them to be fixed in the proposal. The first thing is that the proposal currently doesn't actually say what to do if you access an expected, which is valueless due to exception. There's actually nothing in the proposal of what happens. We decided to throw a bad expected access void, simply because that seemed to be the lowest path way of handling that situation. I have no idea what will actually happen in the proposal. Types T and E cannot be constructed into one another, as I was mentioning to the lady in the middle, because this is a fundamental design choice to keep compile times low. So we remove all of the enable if. We don't use enable if on any of the main constructors to stop the compiler having to instantiate stuff. So all it sees is a set of overloads. It's really fast to select the overloads. There's no enable if to be run to select them. It makes compile times much, much, much lower. One of the big reasons I went away from expect in the first place, deployed it into a large code base, and compile times went up threefold. Because expected, the original implementation was so heavy in the metaprogramming that it just murdered compile times. So I ended up coming up with my own thing that didn't do that, and that's where originally outcome came from 3+ years ago. Other deviations, yes. Outcomes fundamental core monadic programming constructs permit implicit conversion from any lesser representative monad into any more representative monad automatically. So because of that, it was much, much easier just to define unexpected type, the type sugar that I was mentioning earlier on, as an expected void E. Because expected void E will always implicitly convert into any expected TE. Now, that's a seriously big deviation. Doesn't matter. The test suite passes. It doesn't notice. It doesn't care. You don't need to worry about it. I think you'll never notice it in your real-world code. It just happens under the bonnet silently. You only notice it in the debugger. So when you're running the debugger's got weird things because template aliasing. That's okay. Finally, we've defaulted error code instead of error condition. That's almost certainly because of the defect I mentioned earlier, and I think I've won that debate, so that's done. We don't implement ordering or hashing operator overloads because of that lovely link there by a senior boost person. that is correct, and you either have to have implicit construction or you must have ordering and hashing. You can't have both that's safe in code. So that's a defect, and I think that's been agreed. Finally, I always define the default copy and move constructors no matter what, even if the type configured is not capable of it. Now, by the way, that doesn't mean that you can't use types that don't have default copy and move. That's completely permitted. You can use those types. It's just that if you try calling stud is copy constructible, you'll get the wrong result coming back to you. The reason why I've done this is because, again, if you turn this on, and by the way, there is actually if-def-out code that enables this, you have to run enable if on every single constructor, every copy constructor, and every move constructor. And that adds compile times quite significantly. So what I did was I created a template member variable. So there's a const expr variable construction that you can go in and you can simply ask it, does the type support copy construction, does whatever else, and that lets you achieve exactly the same thing without impacting compile times. If Boost Peer Review really cares about that, I can turn it back on again. I personally think just use the member variables. There's other features. The documentation was written using the help of Reddit. So I went through 3 complete rewrites of the documentation from scratch because people came along and said, I still don't get the point of expected. So there's now a small book starting from the fundamental principles running right all the way up to the end, and it's really long. But I mean, people read it and go, wow, you should turn this into a book. And I'm like, no. The fact I had to write it at all is just awful. But it's done, it's there, and pages and pages of it with lots and lots of examples. So if you really want to learn more about this, go to the documentation. I have a very full validation conformance test suite. It goes through every single possible combination and tests lots and lots of different stuff. I have these convenience alternatives called outcome, result, and option. These come with stable ABI guarantees because one of the big things you'll find when you're using expected is that you'll end up returning it from a lot of external functions. The trouble with the LEWG expected proposal is that it is currently in flux. So because it's currently in flux and will change, if you're going to use that, you're going to break your ABI whenever the expected proposal changes. These refinements are not going to change. They have a stable ABI, and moreover, the stable ABI is going to be guaranteed. There's a whole lot of infrastructure there that guarantees at commit in the continuous integration stage that the ABI does not change. If it does change, we have lots of cool inline namespaces that automatically permute so that you'll never ever get a linker conflict between old version and new version of outcome. You can mix them in the same binary. And by the way, while this thing's still in beta, it restamps the ABI with the current SHA of the current git commit. So this thing is constantly currently permuting because it's currently unstable. So you can safely use this stuff in your production code right now, and you will not get bitten later on because you're guaranteed to get a linker error rather than getting misoperation like error corruption. So you can rock on. Yes, full-fat monadic programming API. The purists will hate it, but C++ people will love it because it's really, really C++ orientated. Works with C++ exceptions disabled. And of course, yes, cranks and weirdos do want to make a unified error handling system. I have implemented one of those because I am a crank and a weirdo. So if you want to get into my crank weirdo world, you can go and do this, but it's all optional. If you don't want to do it, you don't have to. It does let you unify all of the error handling systems in a large, wide range binary with lots of third-party dependencies into a single system, really, really lightweight with virtually no overhead. I think it's great. I use it in my own libraries to combine error handling from multiple third-party things, and it works great. Okay, so we're out of time, unfortunately, but I knew that this would be the case. I would say that the extensions are basically very straightforward. I'll just quickly go through this. Expected TE is able to do type-based error handling, so where you employ the type system to create type safety for the error code domains. But if you don't need to do that, if you don't care about that, then you have to type more boilerplate, and that's what exactly these extensions solve. So I have a formal empty state, which turns out to be really handy for making low latency construction. Hard coding the possible error types lets you skip boilerplate. You might notice here's a major problem with expected. What happens if your error code up here, if you change this error code in a header file and you forget to change the error code down here in the catch clause? What do you think happens? We fail to catch it. And as a result, your code fails to work. It's one of the small things which is annoying. We don't have that problem with the outcome extensions. Come here. So what you'll see here is we throw directly out. If you try to access this value, there's none of this intermediate type sugar. Just immediately throw out the system error, immediately throw out the bad alleg, and so on and so forth. So that simply works. Yes, it allows move semantics. And at this point, I shall stop. So these were minor puzzles that I was going to work through if we had time. The slides will be up online pretty soon, so you should be fine. There's lots of stuff there about how stuff executes in const-expr, and you only get one single assembler instruction popping out, because the compiler can deduce stuff without actually making any code for it. And there is the final slide. So thank you very much for watching this. I hope you found it interesting and useful. And I'll now take questions. Yes?
Are the exception benchmarks going to be online?
Are the exception benchmarks going to be online? They are already online. They are on the outcome frequently asked questions page. And you can get the source code for executing them yourself in the repo in, I think there's a benchmarks directory in the GitHub repo, so you can get the source code yourself and tinker with it to your heart's content, or check that it's completely wrong. And in fact, I replied with completely lies as my benchmarks, which would probably be the case. Question, yes?
More like a comment or like something that clicked for me during this presentation, which is, my personal opinion is the only valid use case for exception throw is out of a destructor, because that's something that's implicitly called by the API.
Did you just say throwing exceptions out of a destructor?
Yeah. Well, listen. Okay, so anything that's explicitly called in an API, like you can control the signature. You can use expected instead. And given like the performance cost of exceptions and the like implicit nature of them, that you know, it's like why would you do that essentially? Unless I don't see a strong argument for it, and maybe people will yell at me for that. That's fine. But if you have something that's implicitly called by your API, which is a destructor, because or something implemented like RAI style, you have no way of catching and inspecting the error code. You can install ways of doing that by like in your destructor accessing some shared variable and then accessing that after you know something has been destructed. And there's another observation, which is I think the kind of performance issues with error code, which is that it's singleton and it's shared, and then it's like atomic memory fenced, is because you're trying to like message pass between contexts to communicate an error. And so like, yes, there has to be, there's going to be overhead associated with that. Anyway, this is just a rant, I don't know.
No, so the comments made are really lengthy to repeat, but the observation generally was that destructors, returning errors out of a destructor is problematic in C++. I can tell you what I do in my own code. If I find an error in a destructor code path, I terminate the process, because I don't know what else I can do. I try to print something useful like a stack backtrace, but you kind of just have to give up at that point. You have to write your code so that never ever occurs at best. But it's very easy for other programmers who are not me to come along and write code which is basically unsafe. And to test for that is also really tricky. I really wish there were Clang tidy tests that would test this stuff, but it's complex to test for. You have to cross ABI boundaries, see the entire program as a single whole. Maybe one day the tooling will catch up. Any other questions? Last question before you all go? Are you all desperate to get out to lunch? At the back?
The exceptions are motivating to errors in the constructor.
Sorry, you say the exceptions are one way you can do?
The only way happens in a constructor.
The exceptions are the only way of handling errors in a constructor. Traditionally, yes. There are various hacky ways to get around it, which I think are fairly unmaintainable in a large code base. I think for a large code base where you have mixed ability programmers, you just best never have your constructors ever throw, ever. Make them so lightweight that they are just const-expr and they never ever do anything, and then push your error handling into a static initialization function. I hate to say that, because it's really unnatural to write, but it is what it is. All right, I know I've kept you all 5 minutes later, so thank you very much. I'll be up here for questions afterwards.